Hello, Assalamualaikum, my students. Also here, welcoming you again to our unit differentiability. And today we have a topic that is relation between continuity and differentiability. So we are going to depict this relation. First of all, we will start from this theorem, and the theorem is like this. If like you write like this, if a real valued function, if a real valued function f is differentiable at point x is equal to a in its domain, then it is continuous at x is equal to a. The theorem is like it depicts us here that if a real valued function, if we have a function f and the function is differentiable at some point in its domain, and that point is, for example, x, then the theorem says the function is also continuous at this point. So it means differentiability implies continuity. So after that we will check whether continuity implies differentiability or not, but that is not true. That the converse part of this theorem is not true. What that means? That means if we have a function, it is not necessary that the this function, if that is continuous, that must be also differentiable. So that is not necessary. We will also solve that, but post one we will do it here. So now let's prove it. Let f of x be differentiable at x is equal to a. We have already given the meaning of differentiation or this differentiability on graph, and now we know that if this f of x is differentiable at this x is equal to a, then limit x tends to a, f of x minus f of a divided by a, x minus a, exists finitely. We know by the definition of differentiability, if a function is differentiable at some point in this domain, then this limit must exist. So, and that must be also finite. So here I can write this limit x tends to a, f of x minus f of a divided by x minus a. I will take it as L. Why this L is finite value. So now limit x tends to a. What I have to show? I have to show that if this function is now differentiable, if it satisfies this condition, then the function must be also continuous. So I have to show now continuity of a function. So I will take limit x tends to a, f of x minus f of a. This will be equal to limit x tends to a. Here f of x minus f of a divided by x minus a, x minus a. What I have done here, I have just divided this numerator by x minus a, and I have also multiplied the numerator by x minus a. This x minus a and x minus a, this factor will get cancelled, and I will get my certain back. So here it will create no problem. So, but we know that this limit x tends to a f of x g of x, it is equal to limit x tends to a f of x limit into limit x tends to a f g of x. So I can here also I can give the limit to both this function up to here and also this one. So it will be here limit x tends to a f of x minus f of a divided by x minus a into limit x tends to a x minus a. So now you just check here. This is limit x tends to a f of x minus f of a x dot a. I have given it as I have already given that the function differential and I got this thing that this limit is equal to L. So can I write this here instead of this L into limit x tends to a x minus a? We know that we can give the value of limit directly as x is equal to a if we will get the finite value of the function. So here when I will give the value of x as a, I will get the value of this everything as 0, and 0 is finite, so I will give directly the value of this, so I will get this limit. So here it will be a minus a, that is L into 0, and we know that finite value into 0, that is again 0. So after here I got here this limit x tends to a f of x minus f of a equals to 0. Now this limit x tends to a, this is to both this f of x and minus this f of a, but f of a is finite value because it is the value of the function at point a, and there is no x here because we have already given the value of x as a. So this is independent of this limit, this one. So I can transpose it to other side, that will limit x tends to a, which implies f of x. I will get it when I will transpose this, I will get it f of a. So here what I am getting when I am approaching the value of x to a, the function is getting the function is getting turned to f of a, and we know that when this thing happens, by the definition of continuity, the function is at that time continuous at x is equal to a. So hence, by definition of continuity, f of x is continuous at x is equal to a. Hence proved. We had a function that was differentiable at point x is equal to a, and we got now that the function is also continuous at that point. So it means differentiability implies continuity. So hence proved. This was our theorem. Now we will go for the converse part. And the converse part, I am saying that is not always true. Maybe sometimes it will be true that if we have a continuous function that is also differentiable, but it is not possible every time, it is not certain that every time continuity, if a function is continuous, then the function must be differentiable also. So I will give a counter example that will exhibit that the function that is continuity does not mean always differentiability. So you write it as remark. Continuity does not imply differentiability. Continuity does not always imply differentiable. So the good solution, let f of x is equal to modulus of x when x is not equal to 0 and 0 when x is equal to 0. So I have a function given like this, modulus of x when x is not equal to 0 and 0 when x is equal to 0. I will now check whether this function is continuous or not. First I will check whether this is continuous or not. If this is continuous, then we will go for differentiability. So now first f is continuous. How beta? I will give its proof. We know that a function is continuous only if the left hand limit and right hand limit at point x is equal to a are equal. So here I will show this function is continuous at x is equal to 0. So LH, you write here f is continuous at x is equal to 0. So a is here. LHL is equal to, we know that is limit x tends to 0 negative f of x, and that is equal to limit x tends to 0 negative. It means that the values of x are very close to the 0 but less than 0. So when the values of x are less than 0, at that time we know that this modulus x is equal to minus x when x less than 0. So here we have values of x less than 0. So the modulus of x, so the value of the function at that time is minus x. So it will be here minus x. And that will be equal to, we can directly give the value of this x as 0 because we know that by direct method we can do it. So it will be minus 0, that is 0. Similarly, RHL is equal to, that is right hand limit, and we know that is equal to 0 positive f of x, and that is equal to limit x tends to 0 positive f of x. What is the value of f of x when the values of this means x is approaching to 0 but values of x are greater than 0. When the values of x are greater than 0, we know that at that time the modulus of x is equal to positive x. So it will come out as x, and that will be, we can give direct value of that is 0. Hence, you check here, left hand limit is equal to 0 is equal to right hand limit. So which implies left hand limit is equal to right hand limit and is equal to the value of this f of x at point 0, because that is also 0, is equal to f of 0 is equal to 0. Hence we know that when this condition satisfies, then the function is continuous at point x is equal to 0. So we will write here hence f of x is continuous at x is equal to 0. Now we have now this function continuous at x is equal to 0. We will check whether it is differentiable or not. If it is not differentiable, then we can give this example as our counter example that continuity does not always mean implies differentiability. So here, for the differentiability of a function at point A, we must have left hand derivative equal to right hand derivative, or we must have this limit x tends to a f of x, it must exist, and x means this must exist, but it will exist only when the left hand limit and right hand limit are equal. So we will now left hand derivative is equal to limit, we know that is equal to limit x tends to 0 negative f of x minus f of 0 divided by x minus equalist. Here you check values of x are less than 0 but approaching to 0. At that time the value of the function is minus x, so it will be minus x. right here, limit x tends to 0 negative, value of the function when x is less than, that is minus x, and minus f of 0, that is 0, divided by x minus 0, it is equal to minus x divided by x, and x will get cancelled. We will get limit x tends to 0 negative 1, and that is again equal to minus 1, so it will be minus. So our left hand limit, we are getting it as minus 1. Now right hand limit, right hand derivative, that is equal to limit x tends to 0 positive, f of x minus f of 0 divided by x minus, and it is equal to limit x tends to 0 positive, that means the values of x are greater than 0, and at that time the modulus of x is x, so it will be limit x tends to 0, x minus f of 0, that is 0, divided by x minus 0, so it is limit x tends to 0, x minus 0, that is x, x minus 0, that is x, and it will be 1, limit x tends to 0, 0 positive 1, that is again 1, so I am getting now right hand limit equals to 1. I am getting that equal to 1. So here, when we will check these two, we are getting that left hand limit, left hand derivative and right hand derivative, they are not equal. That means left hand slope and right hand slope, they are not same. So when they are not same, then this limit does not exist. Then we cannot find the slope of tangent at point x is equal to a. So here, and this limit x tends to a, f of x minus f of a divided by x minus a does not exist. When this does not exist, then therefore f of x is not differentiable at x is equal to. So when this thing not here, then x is not differentiable at x is equal to. Hence prove, hence continuity does not mean always differentiability, because we had a function that was, we have a function that was this f of x modulus of x, and we got this function is continuous at point x is equal to 0, but the function is not differentiable at x is equal to 0. And this was our remark, and it's all about the relation between this continuity and differentiability. Now we will solve some examples, and after that we will go for the methods that will help us to find this differential coefficient or derivative. That will be on next lecture, but here we will solve some examples. Example number, first you write down, show that f of x is equal to x square for x less or equal to 0, and f of x equals to x for x greater than 0 is not differentiable at origin. Origin means at 0. So solution, you write down like this. We have a function f of x, and that gives us f of x gives us x square when the values of this x are less than 0. But it gives us f of the as identity function f of x is equal to x when the values are greater than 0. So here we have, you write down, we have f of x is equal to this x square, so that x less or equal to 0, and then we have x greater than 0. Now what you have to do, you have to find out the left hand limit and right hand limit, left hand derivative and right hand derivative at x is equal to 0. And if the left hand derivative and right hand derivative are equal, then it is differentiable. If they are not equal, then it is not differentiable. So you first Now left hand derivative equals to limit x tends to 0, negative, divided by x minus 0. Yes, it will be equal to limit x tends to 0, negative. F of x, when the values of x are less than 0, this is means negative means values of x are less than 0. At that time we have x square, so it will be x square minus f of 0, that is again x square, and we know that when the x is equal to 0, that means f of x is equal to at that time x square, but we have to put the value of x as 0, so that means f of 0 is equal to 0, that will be 0 square, that is 0. So f of value is equal to 0 divided by x minus 0, that is x. So here it is limit x tends to 0, x square divided by x. X and x, that will get cancelled, and we are getting limit x tends to 0, negative x. And we can substitute here by direct method this value of x as 0, so it will come out as 0, that is. So left hand derivative we are getting equal to 0. Left hand derivative equal to 0. Now right hand derivative, that is equal to limit x tends to 0, positive. F of x minus f of 0 divided by x minus 0. So it will be limit x tends to 0, positive. F of x, what is that? When the values of x are less than, greater than 0, at that time the value of the function is x square. X square. And when the value of x is 0, that time the value of function is again x square, and that is 0 square, that is 0 divided by x minus. When the value of this x is greater than 0, at that time we have the value of the function as x only, and when the values of this x are equal to that time we have, so that is 0, x minus 0, so it will be limit x tends to x divided by x, that is 1, so it will come out as 1. So our left hand limit is 0 and right hand limit is 1. So clearly limit left hand derivative and right hand derivative, they are not equal. When the left hand derivative and right hand derivative are not equal, then at that time the function is not differentiable. So this was all about, so this function is not now differentiable, so this was all about the example number first. Write down the second example, that is f of x equals to greatest integer of x, and we have to check this function, whether this function is differentiable at x is equal to 2 or not. We have to check if we have a function f of x as this, is this function differentiable at x is equal to 2 or not. So and you can also check for you have to check this function, whether this function is continuous at x is equal to 2 or not. So I can check this as differentiable by the limit hand derivative, and I will find out the right hand derivative. If they are not equal, then I can say the limit does not exist. But we know that by the theorem, if the function is not continuous, then the function is also not differentiable. If the function is not continuous, then the function is not differentiable, because differentiability always means continuity. So we can here only find whether the function is continuous or not. If the function is continuous, then we can go for differentiability condition, that is left hand limit derivative and right hand, we can find them. But if we have this function not continuous at x is equal to 2, then we can directly say that this function is not continuous, so it must not be differentiable also. So here by the theorem I have given you, so here I will first check continuity. So you write we have left hand limit is equal to limit x tends to negative f of x, that is by the substitution method limit as tends to 0 positive f of this 2 minus h, and this is equal to the we have this f of 2 minus h. While we know that this h is very small, so this if we have this 1 and this is our 2, we know that this 2 minus h is between this 1 and 2, and by the greatest integer function, the value of the function this f of 2 minus h is the greatest integer that is less than this 2 minus h. So here if we have this 2 minus h between this 1 and 2, so for example this is 2 minus h. What is the greatest integer that is less than this 2 minus h? That is 1. So the value of the function at this it will be 1. So here limit as tends to 0 positive, that is 1. So it will be 1. Now right hand limit equals to limit x tends to 2 positive f of x. So it will be by the substitution method, it will be limit as tends to 0 negative f of 2 plus h. So this 2 plus h, that means this 2, the integer 2 is getting additional value h, but the h is very small, so it will be like if this is 2, this is 3, then this 2 plus h will be the point between these two. So what is the we know that the function f of x it is greatest, and the value of this function at x is greatest integer less than x. So we have this the value of this function at this point greatest integer, but that is less than 2 plus h. What is the greatest integer that is less than this 2 plus h? That is 2. So it will come out as limit as tends to 0 negative 2, that is 2. Hence we have left hand limit that is equal to 1 and right hand limit 2. That means they are not equal. Left hand limit, right hand limit. When the left hand limit is not equal to right hand limit, we know that at that time the function is not continuous. So hence f of x is equal to greatest integer of x is not continuous. And when this is not continuous, therefore by above theorem जो हमने proved, above theorem f of x is not differentiable also. So similarly you can do more examples and you can check whether they are continuous or whether they are differentiable or not. So for you I am have so you just concentrate here. For you I will let some examples, so you have to do them at your home. The first example you take as this f of x equals to modulus of x minus 2, and you have to check this is whether this is differentiable or continuous at. So you check this f of x is continuous. You have to show that this is continuous at x is equal to 2 but not differentiable. This function. Second one you take as one plus x, 5 minus x, x less or equal to x greater than 2. You have to check this is not differentiable at x is equal to 2. So this one also you have to do. Similarly, you can go for this. No, you just these two you have to do at your home, and tomorrow inshallah I am going to check these two, and I hope you will make these two. So thanks. We will go for some more topics tomorrow, but today we will stop here.